Good afternoon. I'm Sunhyeok Lee from Korea Advanced Institute of Science and Technology, KAIST. Today, I'll present our work on robust unsupervised domain adaptation through negative view regularization. Thank you for joining us at WACV 2024. Unsupervised domain adaptation addresses the domain gap between different data sources, a challenge when applying models trained on source data to a target domain. This often leads to reduced accuracy, known as the domain shift problem. Our aim is to improve target domain performance by effectively using both labeled source and unlabeled target data, saving on labeling costs. We focus on the concept of patch-based negative augmentation introduced in supervised classification settings. This approach produces negative views where local features are maintained, but global features are disrupted. But Bayesian transformers inherently process images in patches. They show an interesting phenomenon with these negative views. They tend to classify these views with high accuracy, indicating a potential over dependence on local features. This observation in prior research leads to a consideration of methodologies that reduce this reliance and enhance the focus on global features. Transitioning from supervised to unsupervised domain adaptation settings, our study investigates the use of transformers trained with UDA methods. Our experiments reveal a phenomenon akin to the one observed in supervised settings, as shown in the figure below. We hypothesize that applying negative views in UDA can significantly boost transformer robustness and UDA performance. Our aim is to enhance transformers in this domain by shifting their focus from local to global features, improving their effectiveness in challenging environments. Also, our paper introduces a dataset related to unmanned retail shops, addressing challenges in product detection and classification. Given the frequent changes in retail, collecting noisy real-world images for training is costly. Our alternative involves using lab-captured clean images as the source domain and real-world noisy images as the target domain. This approach highlights the domain gap challenge, particularly with occlusions and motion blur, and how UDA methods can effectively bridge this gap. I'll briefly explain our proposed negative view-based contrastive regularizer, or UDA. The NVC regularizer uses a contrastive loss to make transformers focus on global features in the target domain. Negative pairs are each target domain image with all negative views, and positive pairs created through positive augmentations, and consist of positive view and its original image. Our NVC regularizer loss includes positive pairs in the numerator and all pairs in the denominator to enhance the adaptation. And I'll discuss the Retail 71 dataset we propose. This dataset consists of a source and a target domain. The source domain includes clean images captured in the lab setting. The target domain comprises noisy images collected from the real world. The primary factors causing the domain gap are hand occlusion and motion blur. These factors distinguish our Retail 71 dataset from other UDA benchmark datasets. All samples in the test dataset belong to the target domain. We've organized the dataset into 3 levels of difficulty: easy, medium, and hard, with 50 samples per class for each level. For comparison experiments, we used CAT, a state-of-the-art UDA method, as our baseline. We enhanced the method with our proposed MVC regularizer. Although our paper includes results for 4 benchmark datasets, including our Retail 71 and Office Home Office 31 and Vista 2017, we will primarily discuss the results from Retail 71 dataset. Here are the benchmark results from the Retail 71 dataset. When using only clean source images, we noticed low accuracy in real-world settings due to the occlusion and motion blur. When applying UDA methods, we can see the overall accuracy improvements. Specifically, combining SDAT with our MVC regularizer showed a performance boost. Further performance improvement was observed when applying our proposed rule-based synthesis technique, aiding in smoother adaptation. And we also introduced a new negative confidence score metric to evaluate how well the model discriminates against negative views. It involves calculating the average score for the ground truth class across all negative views. So ideally, this score should be low, indicating effective discrimination against negative views. For example, in the Retail 71 dataset, the ideal average negative confidence score is 1/71 classes. Our experiments showed a significant improvement in this metric when using our method compared to the baseline, which indicating enhanced model performance against negative views. Let's look at the Disney visualization results also. With ViT trained only with the baseline method, negative views showed a distribution similar to the original target samples. This result indicates a high dependence on local patch features from negative augmentation, though they're high accuracies. However, when trained with both the baseline and our MVC regularizer, ViT effectively differentiate negative views from original target domain samples. This suggests that ViT is capturing more contextual information and enhancing its robustness. Here's the conclusion. First, we proposed the MVC regularizer to reduce the dependence on local features and enhance the robustness of ViT in UDA settings. This enables ViTs to focus more on globally meaningful features in unlabeled target domains. Also, we introduced Retail 71 dataset, which is a new UDA benchmark dataset. It allows us to assess how robust models are to hand occlusion and motion blur. Our method complements other UDA methods, enhancing overall performance and robustness. Thank you for attending this presentation. For more details, please join us at our poster session. We're eager to discuss further and answer any questions. See you there.